In this video, I'm going to demonstrate how to perform a Friedman's Anova on data that are substantially skewed. Now, the data actually don't really matter whether they are skewed or ranked originally, as in a previous example, because Friedman's Anova will rank the data whether they are in ranked format or not. So ultimately, it doesn't matter whether you're using a non-parametric statistic like Friedman's Anova because the data are skewed or because the data are ordinal in nature to begin with. So in this example, which is the serial murder disposal study, we can see that the data were actually quite substantially skewed. Particularly from memory, it was body 1. So let's look at these data. These are the raw scores over here from body 1 to body 6. And we click on statistics to see some basic descriptives. And here we are with the descriptive statistics. So the distance traveled for the first body was 31.8 kilometers, and we can see there's a progressive increase in the distance traveled to dispose of the body from body 1 to body 6. And we can see that skew was a quite substantial value of 2.1 in the first distance traveled for the first body. Now, skew reduced over time, but the fact that it's above 2 does raise concerns that a parametric statistic would be appropriate in this case. So a person might be inclined to analyze the data with Friedman's Anova to test the hypothesis that mean ranks are equal across the disposal in terms of body from 1 to 6. So in order to perform a Friedman's Anova, click on Analyze, Non-Parametric Tests, Legacy Dialogues, and K-related samples, and put the body 1 to body 6 variables in the test variables box, and you can click on Friedman's and Kendall's W. I mentioned in another video, the wine testing one, that if you just click on Kendall's W, you'll get the Friedman's Anova chi-square value automatically, and you get the estimate of effect size. So I'm going to deselect Friedman's, even though you could click both and you'll get both outputs. So click on OK, and here are the mean ranks, which are showing a essentially linear increase, 2.88 to 2.97, all the way up to 4.5. So these increasing rank values suggest that the distance traveled is increasing across bodies. And we can see that the null hypothesis of equal mean ranks has been rejected with a chi-square value of 43.429, 5 degrees of freedom, and p less than 0.001. The null hypothesis is rejected because the p-value is less than 0.05. Now this chi-square value is what you would get from the Friedman's Anova. SPSS just gives it to you with the Kendall's W as well. And the Kendall's W in this case is estimated at 0.122. Therefore, about 12% of the variability in the ranks is accounted for by which body has been disposed of. So that's a fairly large effect in the behavioral sciences, and that Kendall's W is statistically significant. Now, whether you'd want to follow up with a series of multiple comparisons would be your decision. You could follow it up with a series of Friedman's Anovas afterward, and you would have to be careful of increasing your family-wise error rate in that instance. In the textbook, I actually transformed the data into ranks, and I decided to do a trend analysis as well as a quadratic effect, which I think is now I also applied bootstrapping in that case, which I think is a particularly attractive approach to evaluating the effect in these data. But this would be a perfectly fine way to do it as well, just the traditional Friedman's Anova, testing the equality of these mean ranks, and that hypothesis, that null hypothesis, has been rejected.